Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh dan salam sejahtera. Okay, so today we will continue our discussion on chapter 4, sinusoidal steady state analysis. Okay, this is our last subtopic in chapter 4, which is our part 7, okay, which is Thevenin's and Norton theorems. Okay, so for learning outcome, after completing this lesson, you will familiar with the Thevenin theorem and be able to apply it to reduce any linear two terminals series parallel network with any number of sources, okay, to a single voltage source and series impedance. Okay, number 2, you will become familiar with the Nortons Theorem, okay, and be able to apply it to reduce any linear two terminal series parallel network with any number of sources to a single current source. Okay, this is for single current source and a parallel impedance. Okay, so this is the main content of this topic. Okay, first of all, we will discuss about Thevenin's theorem. Okay, number 2, we will discuss about Norton's theorem. Okay, this is the important theorems in circuit analysis. Okay, we have Kirchhoff voltage law, we have Ohm's law, we have Kirchhoff current law. Okay, so another important theorem, we have a Thevenin's theorem and Norton's theorem. Okay, for circuit analysis. Okay, first of all, we will discuss about Thevenin theorem. Okay, we need Thevenin theorem. Okay, Thevenin theorem basically is a very interesting theorem. Okay, in that it permits the reduction of complex networks to a simpler form for circuit analysis and design. Okay, this is the important reduction of the complex network to a simpler form, okay, for analysis and design. Okay, Thevenin theorem states the following: any two terminal of network can be replaced by an equivalent circuit consisting of a voltage source and a series impedance as shown in the figure below. Okay, let's say you have a network. Okay, so we have any terminal. Let's say you have a and B terminal, so it can be replaced, this network, okay, this complex network can be replaced by equivalent circuit. We call it a Thevenin equivalent circuit, which is consists of VTH, V Thevenin, and Z Thevenin. Okay, this is the definition of Thevenin's theorem. Okay, you can replace this complex network by VTH, V Thevenin, and ZTH. The question is how to replace this complex network to the VTH and ZTH. So we will discuss in this subtopic. Okay, look at the example. Okay, by using Thevenin theorem, find current IT. Okay, you need to find IT. Where is IT? This is IT. Okay, you need to find IT. How to determine current? By using Thevenin theorem. Okay, given voltage supply, and then this is a current supply, and then you need to find the current here by using Thevenin theorem. Okay, so first of all, what you need to do, okay, first you need to determine the phasor domain of the circuit. Okay, phasor domain circuit. Okay, then you need to convert all Vs, Is to the phasor form or to the polar form. Okay, Vs, okay, we have Vs, we have Is, and then Zl, this is a Zl, you need to convert to polar form J omega L. Okay, similarly to Zc equal to 1 over J omega C. Okay, so once you convert from a time domain to the polar form, and then what you need to do, you need to transform your circuit to the Thevenin equivalent circuit. Okay, the given circuit can be transformed into a simple series circuit. Okay, if you want to determine a current, sekarang awak nak determine current okay, so you can transform this circuit in the box to the Thevenin equivalent circuit. So we have a terminal. Okay, look at to this circuit. You have a terminal. Let's say this is a terminal A, and then this is a terminal B. So this circuit in the box you can replace with the Thevenin equivalent circuit. So the question is how to replace this circuit in the box to the Thevenin's equivalent. This is what we want to learn in this topic. Okay, so you have a terminal A and B. Okay, first what you need to do, okay, you need to mark, okay, the two terminal. Okay, this is the terminal A and B. Okay, this one A and B, we marks to A and B. Okay, two terminal, any point of the two terminal, okay, of the box, and assign the direction, okay, to the voltage and terminal currents. Okay, this is a terminal currents I, and this is a voltage, direction of voltage, which is VAB, the potential difference between A and B. Okay, next what you need to do, okay, this is the important step. Okay, this is the important step for the Thevenin concept, Thevenin theorem. Okay, first you need to calculate the Z Thevenin. Okay, in the Thevenin transformation, we need to calculate Z Thevenin and V Thevenin, voltage Thevenin. Okay, how to calculate Z Thevenin? We call it a ZTH. Okay, what is the definition of ZTH? ZTH basically is impedance seen from point A and B. This one we call it Z Thevenin. Okay, how about this? Because in this circuit we have a source. What happened to the source? Okay, then you need to replace, you need to set all the source to the zero. Okay, source to the zero. Okay, in this circuit we have a current source. I equal to 0 means current equal to 0 means open circuit. That's why we set to the open circuit, because we have current source here. So I equal to 0 equal to open source. Okay, let's say you have a voltage. Let's say you have a voltage source here. So voltage equal to 0 means short circuit. If you have voltage source, okay, you make it voltage equal to 0, it means that you replace by a short circuit. Okay, and then current equal to 0 means open circuit. I equal to 0 equal to open circuit. Okay, so then you can calculate the ZTH. ZTH means a total impedance seen from point A and B. Okay, so in this case ZTH equal to ZAB. Okay, ZTH equal to ZAB. So ZAB equal to 25 ohm in series with minus J125. This is your ZTH. Okay, after you got ZTH, then you need to calculate VTH. Okay, VTH, voltage Thevenin. Okay, first returning all the source. Okay, you need to return in all the source. You need to connect with the existing source. Let's say in this circuit we have a current source. Connect back to the circuit to their original position, and then finding the open circuit voltage between the pair of input terminal. Which means you need to determine the voltage at this terminal, A and B terminal. Okay, by analyze this circuit, you can determine voltage across here. Okay, how to determine voltage across here? Since here open circuit, so VAB equal to VCD. Okay, VAB equal to VAC plus VCD. In this case, VAC equal to 0, because there is no current here. Okay, according to this circuit, I equal to 0, so equal to VCD. So how to determine VCD? VCD equal to, VCD. This is a positive, this is a negative. Okay, VCD equal to I, this is current. We have current times by ZC. Then you got VCD. So V Thevenin equal to VAC, of course, equal to 0. So equal to VCD. So you got voltage. This one we call it a Thevenin voltage. Okay, Thevenin voltage. Next, what you need to do, you need to redraw the original circuit. Okay, redraw the original circuit, but with circuit in the box now replaced by Thevenin circuit. Thevenin equivalent circuit. Okay, you have this one, your circuit in the box, you replace with the Thevenin circuit. This is your original one. Okay, V SL connected with the ZTH and VTH. Okay, this is the position of currents. Okay, so now you have a series circuit, so easy for you to determine current. Okay, so that you can determine current. Next, you can determine current I by applying KVL. Okay, KVL. You apply KVL here, then you can determine current. So current equal to V minus VTH divided by total Z. Okay, by applying KVL. Or if you want to do step by step, negative minus Vs plus I times Z plus I times ZTH. Okay, and then plus VTH. By solving equal to 0, by solving that equation, KVL equation, so you can determine current. Okay, is it clear? Or if you maybe I think you are already expert with the KVL, so you can determine the current equal to voltage difference Vs minus VTH divided by Z. Okay, so you got current, and then in polar form, then you can transform to the time domain. Okay, is it clear? This is example on how to apply Thevenin theorem. Okay, for solving the for analyze our circuit. Okay, next we discuss about Norton's theorem. Okay, Norton's theorem. Okay, this theorem states the following: any terminal linear to terminal AC circuit AC network can be replaced by an equivalent circuit consisting of a current source and a parallel impedance. Let's say you have a linear circuit, okay, and then you have a two terminal A and B. This circuit you can replace by Norton equivalent circuit. Okay, Norton equivalent circuit, we have a IN, we call it a Norton current, and then we have Zn, Norton impedance, okay, in parallel with the IN, okay, and then this is a terminal A and B. So this one we call it a Norton equivalent circuit, okay. Okay, so the question is how to apply this Norton equivalent, how to apply this Norton theorem. Okay, look at to the example. Okay, use Norton theorem to find current IT. Okay, you have a circuit. Okay, you need to find, let's say, this IT by using Norton theorem. So how to apply Norton theorem for solving IT? Okay, so you have a current source here, and then you have a voltage source, and then you have a LR. So how to apply Norton theorem for solving IT? So first of all, what you need to do? Yeah, you need to set this one as a in one box, and then you can replace by Norton equivalent circuit. Okay, so first you need to convert from time domain to phasor domain. Okay, convert this one voltage, current, XL, XC to the polar form. Okay, you convert ZL. Okay, you determine ZL, ZC, VS, and IS in polar form. Okay, we call it a phasor equivalent circuit. Then, okay, you determine IN and ZN for this circuit at this point. At this point, okay. At this point, you need to replace with Norton impedance and IN. Okay, Norton current. Okay, so you replace the circuit in the box with the Norton equivalent. We call it a Norton equivalence. Okay, how to replace? How to determine? Norton equivalent. First, you need to determine R Norton. Okay, first you need to determine, sorry, not R. You need to determine Z Norton. Okay, impedance of the Norton. So how to determine Z Norton? Which is exactly equal to how to determine the Z Thevenin. Okay, what we need to do, we need to set all the source to the 0, which is a voltage source are replaced by short circuit and current source replaced by open circuit. Okay, how to determine Z Norton? Z Norton actually seen from this point, this A and B. Okay, seen from this point to our box. Let's say, and then we need to determine Z Norton. In this case, Z Norton equal to ZTH. Okay, Z Norton equal to ZTH for this circuit. Okay, so how to determine Z Norton? So we replace our voltage source by short circuit. Then we can calculate Z Norton. Z Norton in this case, seen from here, we have a series combination of R and ZL. Okay, Z Norton. So you get Z Norton, and then you need to determine I Norton. Okay, I Norton. Okay, what you need to do? You need to first return all the sources. We have a voltage source. We need to connect back to the circuit, to the original position, and then find the short circuit current between two marked terminal. Basically, we need to determine short circuit current from point A and B. Okay, this is the direction. Okay, from A to B. We call it I short circuit. This I short circuit equal to I Norton. I Norton. Okay, so how to determine current? Okay, you can solve by using KVL. Okay, voltage divided by total Z. We have voltage divided by total Z. Okay, so and then you can get a current. So I short circuit equal to I Norton. This I short circuit basically equal to I Norton in Norton equivalent circuit. Okay. Okay. This is the transformation from the Thevenin to the Norton. Okay, if you determine V Thevenin, you can also determine I Norton by using this transformation, because I Norton equal to VTH divided ZN, Z Norton. Because in this case, we know that Z Norton equal to ZTH. Okay, go back to our example. Okay, so now you have I Norton. So next, you can draw the Norton equivalent circuit, taking particular care to draw the error symbol of the source pointing in the right direction. So what you need to do, you need to draw the Norton equivalent circuit that connected to point A and B. Okay, so this is the direction of the Norton. Okay, IN. Okay, this is your IN, this is your ZN in parallel with the current source, which is IN. Okay, connected to the point A and B. Okay, next you can draw the original circuit. Okay, you have a Norton equivalent circuit connected to the point A and B. So this point A and B connected to the original circuit. Okay, so what you need to do, you want to find basically is you want to determine I. How to determine current? And now you have a simple circuit. Okay, you can easily determine current by using current Kirchhoff law, KCL. Okay, you have a ZC, you have a ZN, you have current source. You can determine current by using KCL. Okay, you have a IN and then you have a ZN. Then you can determine current. Okay, these two current, you have a current, let's say this is I1, this is I Norton. You can combine. You can combine together because this is in one node. You can combine together. Let's say you call it the combination of this. Let's say this is I1 plus IN equal to IS. IS equal to I1 plus IN. So you have it become one current source. So you have a ZC and then you have ZN. So then you can apply KCL to determine I. Okay. Sorry, you can use current divider. Okay, you can use current divider to determine I. Okay, previously we already discussed about current divider. You have a current source, you have a ZC, and then you have ZN. Then you can determine current through the ZC. So I equal to Zn divided by Zc plus Zn times total current. okay, enter to the terminal. Okay, this is the concept of current divider. So you got a current in polar form, then you can convert to rectangular form. Okay, is it clear? This is the approach. This is the application of Norton theorem. Okay, we try to solve the complex circuit and then make it a simple circuit. Then we can apply the existing theorem, for example, current divider, Kirchhoff voltage law, Kirchhoff current law, for solving our circuit. Okay. Next, we look at to the source transformation concept. The source transformation is the replacement of a Thevenin equivalent circuit by Norton equivalent circuit, which means you can transform your source from Thevenin equivalent circuit. Let's say you have a Thevenin equivalent circuit, you have a VTH and ZTH. You can transform to the Norton equivalent circuit that consists of IN and ZN. So from VTH and ZTH, how to determine IN? IN equal to VTH divided by ZTH. How to determine Z Norton? We know that Z Norton equal to ZTH. Okay, that's the way lah how to transform from Thevenin to the Norton equivalent circuit. Let's say you have a Thevenin let's say you have a Norton equivalent circuit. How to transform to a Thevenin equivalent circuit? You have a IN and ZN. Then you need to transform to Thevenin equivalent circuit. How to determine VTH? Okay, ZTH equal to ZN, and then VTH equal to ZN times IN. Okay, that's the way how to transform from Thevenin equivalent circuit to the Norton equivalent circuit, or vice versa. Okay, look at to our last example. Okay, by using Thevenin's theorem, find current I1 and I2. Okay, this is I1. This is I1. Okay, so this is I1, and then this is I2. So this one I2. Okay, by using a Thevenin theorem. So basically, you can solve this circuit by using mesh analysis or nodal analysis. Okay, or in others method, you can solve using Thevenin theorem. So how to solve this circuit by using Thevenin theorem? Okay, to find I1 and I2. Okay, so next, what you need to do? First, we determine I1. Okay, in order to determine I1, you can replace this circuit by Thevenin equivalent circuit, this box. Okay, you can put box here, and then we can determine Thevenin equivalent circuit. Okay, first we determine I1. Okay, this one. In order to determine I1, this is I1. Okay, then you can make it this one as a board, as a one box, as a box. Then you can determine the VTH and ZTH from this terminal A and B. Okay. Okay, number 2, you can determine Thevenin voltage. Okay, how to determine Thevenin voltage? First, you can determine the Thevenin voltage. Okay, it's just simply to open circuit voltage, basically equal to VAB. What is the value of VAB? You can solve by using voltage divider. We have a voltage source here connected to SL and J connected to the XC. And then how to determine VAB? VAB equal to voltage cross here by using voltage divider. This is the application of voltage divider. Okay, voltage divider equal to minus JXC divided by JXC plus JSL. Okay, times voltage input. Okay, you got the VTH. And next, you need to determine ZTH. Okay, Z seen from here. Okay, determine the Tiffany's impedance. We call it as ZTH. Seen from here. So in this case, okay, this is open. This is open circuit. So this one connected to J4. So parallel, minus J2 parallel with J4. Then you got a ZTH. Okay, which means minus J2 parallel with J4. Okay, and then make sure in order to determine a Thevenin impedance, we need to set, let's say we have all the source connected to this circuit, we need to set to the 0. Okay, if we have a voltage source, when voltage equal to 0, it's become short circuit. That's why we have a short circuit here. So ZTH, you got ZTH. And then you redraw your circuit, okay, then connect to the original circuit. This is the original circuit, okay, connected to the ZTH and VTH. Okay, once you have a ZTH and VTH, then you can determine current by using KVL, by applying KVL. Okay, KV minus VTH divided by Z, or you can write one by one or step by step. Okay, minus V1, okay, plus, okay, I1 times in bracket 8 minus J4, close the bracket, okay, and then plus VTH equal to 0. Okay, if you are familiar with the KVL, so you can directly write KV minus VTH equal to minus minus become positive divided by total Z. Okay, then you can get I1. Okay, this is I1. Okay, so you have done for I1. So next you can determine I2. Okay, this is I2. This is the direction of I2. So the step 1, you can replace all this circuit by box. Okay, this is the terminal A, this is your terminal A and B. Then you can determine VTH and ZTH for this circuit. Okay, first of all, you need to determine VTH. Okay, for this circuit, you need to determine VTH. Okay, what is the voltage across this A and B? Then you can apply Thevenin. You can apply voltage divider to determine voltage across A and B equal to voltage across ZC. Okay, so by using voltage divider, okay, voltage divider, and then you get VTH. Then you need to determine Thevenin impedance. Okay, Thevenin impedance, how to determine Thevenin impedance? You set all the sources to the 0. In this case, we have a voltage source here, so we replace to the short circuit. So what is the Z Thevenin? Z Thevenin equal to minus J2 parallel with 8 ohm. This is your Z Thevenin. And then you can replace the circuit in the box with the Thevenin equivalent. Then you can connect your Thevenin, VTH and ZTH to the original circuit at point A and B. And then you can determine I2 by using KVL. So at this direction, so V minus VTH divided by total Z. Then you can get I2. Okay. Is it clear? So I think that's all for Thevenin theorems and Norton theorems. I hope you can understand the concept of Thevenin's theorem and Norton theorems, okay, for solving our circuit analysis, okay, for applying in the circuit analysis. Okay, I think that's all for today. Okay, Assalamualaikum warahmatullahi taala wabarakatuh.